Hello, this is Vivian Chan. In this video, I'm going to explain to you HSC year 2018 Mathematics Extension 2, question number 7 and 8. Question number 7, it is about a complex number. The question asks you to locate all the complex numbers C with the property that the argument of Z is equal to the argument of C plus 1 minus I. Before we study to this question, let's do some revision on complex number. Say we have two complex number C1 and C2 as indicated, and we can always locate these two complex number on a rectangular coordination plane. Let's say Z1 is here. What is the argument of Z1? We are talking about from the origin, we draw a vector to Z1, and we are measuring the angle between the vector and the horizontal in an anti-clockwise direction, and this is the positive value. Of course, this value is not unique. Let's say the angle here is measured as theta, and you can make it to be theta plus 2 pi or theta plus 4 pi. So if we are just asking for the argument of a complex number, it can be many different values. Therefore, we set the principal value of an argument of a complex number to be in between minus pi and pi. Let's come back to the complex number Z1 here. How to find out the theta? It is the arctangent of y1 over x1. And now let's mark C2 on the plane. What is the meaning of Z2 minus Z1? And what is the meaning of argument of Z2 minus Z1? For complex number C2 minus Z1, we are talking about starting from Z1, we draw a vector to Z2. This vector is Z2 minus Z1. And what is the argument of Z2 minus Z1? We are talking about the angle between the vector and the horizontal measured in anti-clockwise direction. Therefore, this is the argument of C2 minus C1. Now, that's all we need to know for this question. Here's Z plus 1 minus I. We are always interested in one complex number minus another complex number. Therefore, we change it to Z minus another complex number, which is minus 1 plus I. And let's locate this minus 1 plus I here. The question is asking for locating all the complex numbers Z anywhere on this plane. Let's say it's here. And the C must satisfy the properties of the argument of itself, which is this angle, must be equal to the argument of Z minus 1 plus I, this angle. Of course, these two angles are not equal, and this Z cannot be the Z that's required in this question. How can these two angles be equal? In order for these two angles to be equal, this Z, the minus 1 plus I, and the origin, the three should lie on the same straight line. Now, on the straight line, I can take any Z I like. Say I take Z here, and the argument of Z is this one. Argument of Z minus 1 plus I is this one. Of course, these two arguments are the same. We still have some problems here. We cannot take the Z to be this minus 1 plus I. It is so obvious because argument of this Z, if we take it to be minus 1 plus I, then argument of minus 1 plus I cannot be equals to 0, right? Therefore, you cannot include this point. And then you cannot also take the origin because the origin is 0. If we talk about Z equal to 0, first of all, we don't define 0 for argument. And then the argument of 0 is definitely not equal to the argument of 0 minus 1 plus I. But how about the red part of this straight line? Can we take the Z from here? Seems not, because let's say if I take the C here, then the argument of C should be this one. But the argument of Z minus 1 plus I should be this one. This is a negative value, while the argument of Z is a positive value, and they cannot be equal. How about if I take a C from this part of the straight line, say here, it is okay because the argument of Z is this angle. It is measured in a clockwise direction, therefore it is a negative value. But the argument of Z minus 1 plus I, it is also a negative value, and these two arguments are equal. This part of the straight line is okay, therefore the answer is D. Question 8. The question gives you the curve of y equal to fx, and then it defines the primitive function of fx to be the capital Fx and the gradient of ft dt from 0 to x. The question asks to locate the points on the function y equal to capital Fx where the curve changes its concavity. Talking about concavity, we have to locate all the points of this function for their second derivative equal to 0, and then check for those points and see if they are changing the concavities before and after that particular values. According to the definition of capital Fx, the first derivative of capital Fx should be equals to small fx, and the second derivative of capital Fx should be equals to the first derivative of the small fx. Therefore, here capital double prime x equal to 0 is talking about the first derivative of fx equal to 0, which is located at x equal to a, c, or d. And then let's check for the concavity before and after a. Before a, the first derivative of fx is a positive. And after a, the first derivative of small fx is negative. Therefore, the concavity of capital Fx is changing from concave upward to downward. Similar for point C, the first derivative before C is negative and after C is positive. Therefore, the concavity of capital Fx is also changing at C from concave downward to concave upward. But for point D, the small fx at D, the first derivative is positive before D and still positive after D. Therefore, fx is not changing its concavity at point D, and the answer is B.